In the realm of computer graphics, the pursuit of realism knows no bounds. Artists and developers constantly strive to create digital worlds that mirror our own with breathtaking fidelity. At the heart of this endeavor lies physically based rendering, PBR, a revolutionary approach to rendering that has transformed the way we create and experience computer-generated imagery. PBR marks a paradigm shift from traditional rendering methods, eschewing artistic approximations in favor of a physically accurate simulation of light and materials. By grounding itself in the principles of physics, PBR produces images of exceptional realism, blurring the line between the virtual and the real. The importance of PBR in modern computer graphics cannot be overstated. From blockbuster films and AAA video games to architectural visualizations and product design, PBR has become the industry standard, enabling the creation of immersive and visually stunning experiences across a wide range of applications. This essay delves into the intricacies of PBR, demystifying its core concepts and empowering aspiring digital artists to harness its power. Join us as we embark on a journey to explore the art of realistic rendering with PBR. At the core of PBR lies the concept of materials, the very substances that shape our world. PBR materials are defined by a set of properties that dictate how they interact with light, governing their appearance and ultimately shaping the realism of a rendered scene. First, we have the base color. The foundation of a material's appearance is its base color, representing the diffuse color reflected by the surface. It defines the material's overall hue and saturation, whether it's the vibrant green of grass or the warm brown of wood. Next is metalness. Metalness describes the extent to which a material is metallic. Metals exhibit distinct reflective properties influencing how they interact with light and reflections. A high metalness value indicates a highly reflective surface, like polished silver, while a low value represents non-metallic materials like wood or plastic. Roughness determines the smoothness of a material surface. Rough surfaces, like concrete or sandpaper, scatter light in multiple directions, resulting in diffuse reflections. Smooth surfaces, like polished metal or glass, reflect light in a more focused manner, producing sharper reflections. Then, we have normal vectors. Normal vectors define the orientation of a surface at each point, influencing how light interacts with it. They are crucial for creating the illusion of surface detail, adding depth and realism to otherwise flat surfaces. Lastly, emissive properties determine a material's ability to emit light. Objects like light bulbs, fire, or glowing screens emit light, illuminating their surroundings. This property adds another layer of realism and visual interest to rendered scenes. Lighting is the lifeblood of any rendered scene, breathing life and dimension into digital worlds. PBR relies on physically accurate lighting models to simulate the behavior of light in the real world, resulting in believable and visually stunning results. Different light sources are incorporated in PBR, each with unique characteristics. Common light sources include directional light, which simulates sunlight casting parallel rays from a distant source. Point light emits light uniformly in all directions from a single point, like a light bulb. Spotlight emits light in a cone shape, resembling a spotlight or flashlight. Area light emits light from a defined area, such as a rectangular window or a fluorescent light panel. Each light source is defined by properties that influence its appearance and behavior. Color determines the hue of the light emitted. Intensity controls the brightness of the light source. Fall-off defines how the light intensity diminishes over a distance. PBR accurately simulates the way light interacts with surfaces in a scene. This includes direct illumination, which is light directly hitting a surface from a light source, and indirect illumination, which is light bouncing off other surfaces in the scene, creating realistic shadows and ambient lighting. Rendering algorithms form the backbone of PBR, translating the complex interactions of light and materials into the images we see on screen. These algorithms simulate the journey of light rays as they traverse a virtual scene, interacting with objects and surfaces along the way. Path tracing is a ray tracing technique that simulates the path of individual light rays as they bounce around a scene. It accurately captures the behavior of light, producing highly realistic results with accurate reflections, refractions, and global illumination. Spherical harmonics are a mathematical representation of light that simplifies complex lighting information. They are often used to approximate indirect lighting, providing a computationally efficient way to achieve realistic ambient lighting effects. Physically based shading employs physically based shading models that accurately calculate the interaction of light with a material's surface properties. This results in more believable and predictable shading, ensuring materials respond realistically to different lighting conditions. Section 5. Texture maps. Adding detail to PBR materials. While material properties form the foundation of PBR, texture maps provide the detail and nuance that bring surfaces to life. Texture maps are images that control various aspects of a material's appearance, adding visual complexity and realism. Albedo maps define the base color of a material at each pixel. They are essentially image textures that determine the color and patterns on a surface, such as the grain of wood or the texture of fabric. Metalness maps control the metalness of a material at each pixel, allowing for variations in reflectivity across a surface. This allows artists to create objects with both metallic and non-metallic parts, like a rusty metal object with areas of paint. Roughness maps determine the smoothness or roughness of a surface at each pixel. This allows for variations in microsurface detail, creating more realistic representations of materials like brushed metal or rough concrete. Normal maps manipulate the perceived surface normals, creating the illusion of depth and detail without adding geometry. They are essential for adding fine details like scratches, bumps, or wrinkles to a surface. Height maps are grayscale images that represent the height or depth of a surface at each pixel. They are often used to add large-scale details like mountains or valleys to a terrain, or to create bas-relief effects on objects. Section 6. Essential tools for PBR artists. The rise of PBR has been accompanied by the development of powerful software and tools that empower artists to create stunningly realistic assets and environments. These tools provide intuitive interfaces and advanced features for creating PBR materials, lighting scenes, and rendering images. First up is Blender. Blender is a free and open-source 3D creation suite that has gained immense popularity for its versatility and powerful rendering capabilities. It offers a comprehensive set of tools for modeling, texturing, lighting, animation, and rendering, making it an excellent choice for both beginners and experienced artists. Next, we have Substance Painter. Substance Painter is a dedicated 3D painting application widely used for creating high-quality PBR materials. It offers a node-based workflow and a vast library of materials and tools, allowing artists to create realistic and detailed textures with ease. Then there's Unreal Engine. Unreal Engine is a powerful game engine renowned for its realistic rendering capabilities and advanced PBR features. It provides a complete suite of tools for creating immersive and visually stunning games and interactive experiences. Lastly, we have Unity. Unity is another popular game engine that has embraced PBR, offering a robust set of tools for creating high-quality graphics and realistic materials. It is known for its user-friendly interface and vast asset store, making it a popular choice for both indie and AAA game developers. Section 7. PBR in Practice Tips for Stunning Results. Mastering PBR involves more than simply understanding its technical aspects. It requires an artistic eye, attention to detail, and a willingness to experiment and refine your work. Here are some practical tips to elevate your PBR skills and create stunningly realistic renders. First, use real-world references. Observation is key to achieving realism. Study real-world materials and lighting conditions, paying attention to how light interacts with different surfaces. Use photographs and real-life objects as references for your PBR materials and lighting setups. Next, simplify materials and lighting. While PBR encourages realism, it's important to avoid unnecessary complexity. Start with simpler materials and gradually add detail and complexity as needed. Similarly, focus on creating a balanced and believable lighting setup before introducing intricate lighting effects. Emphasize testing and iteration. PBR is an iterative process. Don't be afraid to experiment with different settings, materials, and lighting scenarios. Regularly, test your work in the renderer and make adjustments based on the results. Iteration is key to refining your skills and achieving the desired level of realism. And lastly, advocate for performance optimization. Realistic rendering can be computationally expensive. Optimize your scenes and assets for performance by using efficient modeling techniques, optimizing your textures, and leveraging level of detail systems to reduce the rendering workload. Section 8. The future of realistic rendering. The pursuit of realism in computer graphics is an ongoing journey, and PBR represents a significant milestone in this pursuit. However, the future of realistic rendering holds even more exciting possibilities as technology continues to advance and our understanding of light and materials deepens. Real-time ray tracing, once a computationally demanding technique, is rapidly becoming more accessible, promising to further blur the line between real-time graphics and offline rendering. Advancements in artificial intelligence and machine learning are also poised to revolutionize the way we create and interact with digital content, enabling the creation of even more realistic and immersive experiences. The future of realistic rendering is bright, and PBR will undoubtedly continue to play a pivotal role in shaping the digital landscapes of tomorrow. As artists and developers, we are only beginning to scratch the surface of what is possible with PBR, and the years to come promise to be an exciting time for the world of computer graphics. Section 9. Conclusion. Embracing the power of PBR. Physically based rendering has fundamentally transformed the way we create and experience computer-generated imagery. By grounding itself in the principles of physics, PBR empowers artists to achieve unprecedented levels of realism, blurring the lines between the digital and the real. From the intricacies of material properties and lighting to the power of rendering algorithms and texture maps, PBR offers a comprehensive framework for creating believable and visually stunning digital worlds. By embracing the power of PBR, artists and developers can unlock new levels of creativity and push the boundaries of what is possible in the realm of computer graphics. As we move forward into the future of realistic rendering, PBR will undoubtedly continue to evolve and inspire new generations of digital artists. The journey towards realism is an ongoing one, and PBR provides the tools and techniques to navigate this exciting frontier and bring our digital creations to life with breathtaking fidelity.